Well, hello everybody. We're going to have a look at three new things today in the area of the normal distribution, and they are, very simply, the standardisation of the normal distribution, the 68, 95, 97, 99.7 rule, and also how to practically determine normal probabilities using your TI handheld wonder machine, okay? Alright, here's the first one, 68, 95, 99.7 rule, and that simply says, here we are, here's a standard normal curve, and it just so happens that, here we go, 68% of values lie within one standard deviation of the mean. That means to the right and to the left combined, okay? That's just over 2/3. That's pretty amazing, isn't it? Within one standard deviation of the mean. Okay, 68%, that's the 68-bit. 95% of values lie within two standard deviations of the mean, which is nearly all of them. And then, finally, we know that 99.7% of all values lie within three standard deviations of the mean, okay, which is nearly everything, okay? So that's how it works, all right? So have a look at it again. You've got 68%, one standard deviation, 95% two standard deviations, and 99.7 three standard deviations either side of the mean, okay? Now we're going to look at a little example to capitalise on this new fact that we have at our disposal. We've got the heights of a large group of 1,000 young male students of a certain age group is normally distributed with a mean height of 100 centimetres and a standard deviation of 15 centimetres. Sounds to me like they're probably in about year 7. Now, okay, approximately what percentage of the distribution lies between 85 and 115 centimetres? And part B, to the nearest student, how many students are taller than 145? Now, come on, you tell me, what would you do? Well, as far as part A is concerned, I think, look, can you read that off? I mean, from 100 centimetres to go back to 85 and then to go forward to 115, you're talking 15 centimetres, aren't you? And that is one standard deviation, right? So therefore, you're talking one standard deviation either side of the mean, which means we are talking 68% of all students. Okay, Mr. Box. Thank you, Mr. Box. Okay, easy as, yeah? Oh, good. Now, part B, for you and me, we need a graph for this. There is the graph of that distribution, and you can see that we've got, here's your 15, that's your dilation factor for the standard deviation of 15, and up here is your mean of 100, okay? That's your dilation factor there, actually, in the x direction. That's your adjustment, shrinking it by a factor of 15 in the y direction to make it to area compensate, so that it's a probability density function again. Alright, we did all that in a previous video. Now, come on, let's go. There's 100, that's the mean, and we're filling in the numbers. That's one standard deviation to get to 115. That's two standard deviations to get to 130, and three standard deviations to get from 100 to 145. Now, going back the other way, now what are we talking? We're talking more than three standard deviations to the right of the mean, aren't we? So, we're talking about that minuscule little tail there. We're talking about this little fella here. The area. It's very difficult to see as an area, but I did my best. It's the area under that curve there, and it's also the area under this bit here would be what percentage of students? What would it be? Come on, we'll work it out. That one plus that one, the two outside areas or tails, they must come to 0.3%, mustn't they? Because this bit inside here, all the rest of it, all the vast majority of the area, excluding those two tails, would be 99.7 according to our rule, wouldn't it? Percent. So therefore, if we're saying, yeah, that's what that comes to. Now, hence if we're, that's right, that's for 100 and more than, then what I'm saying is for more than 145 centimetres, which is only the right-hand side, the right-hand part of the tail only, this part here, okay, Therefore, we must be talking not 0.3, which is both of them combined, but what? Yeah, we're talking about 0.15%, aren't we? 0.15% is this little bit here, okay? Right. You with me? And that's what we want, okay? So now let's work that out in terms of numbers of students. We've got 1,000 students, so we'll go back up here and we'll work this out just in this little space here. So we've got 0.15% of 1,000, that means 0.15 over 100 times 1,000. We're going to cancel the trailing zeros. Goodbye, goodbye. What are we left with? 0.15 times 10, which means we've got 1.5 students. Well, that's a bit crazy. You can't have a half a student. So we'll do it to the nearest student, which would be 2 students, yeah? You happy? That's it, okay? To the nearest student, yeah? All right. Now, we're going to do some standardisation now. That's the Z thing, okay? That's this, this beast here. Z, okay, you find Z by taking your transformed value of X, subtracting mu from it, and dividing all of that by sigma. That takes you straight back to the standard normal horizontal variable, which we've called X. And we had a gala naming ceremony in the previous video of Z, yes? Okay, now this is the good oil on standardisation. Standardising values from a normal distribution back to what I call home base, which is the standard normal distribution, often provides us with this first thing here, which is a means of comparing 2 different distributions from a common basis. In other words, it allows us to compare apples with apples instead of apples with oranges, which doesn't compare, okay, when they're 2 different transformed and pushed around and dilated and translated distributions. You can't really compare them, so you just take them back to home base and then you can look at them both critically and compare one with the other. Yes? And we're going to do that now. And secondly, it allows you to have a means of often determining an unknown mean and or standard deviation for a single distribution given some known data about the distribution which doesn't include the mean and or the standard deviation. It allows you to work it out, and we're going to do that in a later video. That's a little bit advanced, but we'll do the now one now. Okay, here it comes. We've got Michael scoring 85 on a mathematics section of a scholastic aptitude test, the results of which are known to be normally distributed with a mean of 78 and a standard deviation of 5. Cheryl, on the other hand, sits for a mathematical ability test. She scores 27, but wait guys, that's not bad because these test scores are normally distributed with a mean of 18 and a standard deviation of 6. Now, okay, assuming that both tests measure the same kind of ability, and I would like to add and have the same level of challenge, otherwise what's the point of trying to compare one with the other? Who has the better score? Well, you see, it's impossible to work that out with the information that you've got there unless you bring them back to a common basis. Yes? So let's Z them. Da-da-da-da. Come on, Michael, we're going to Z you. That's his Z, and we'll put the numbers in now. 85, which is his score, minus 78, which was the mean, over 5. Standard deviation, what do we get? 7 over 5, okay, 1.4 for Michael. Well done, Michael, that's a pretty good score. That's past the first standard deviation to the right of the mean, which is 0 for the standard normal, isn't it? Now, come on, Cheryl, how did you go? Right, there's Cheryl's situation, and what did she get? She got 20. So what's that come to? 9 over 6. I think the girls have it. 1.5. So yes, it looks like Cheryl has the higher relative score. You see? Now you see why we're Zing things, guys, don't you? Thank you, Cheryl. What a good job you did. Right, that's the first use of standardisation, everybody. It allows you to bring everything back to home base so that you can see what you're looking at and compare. Right, here's another one, another example. This is some tests. Mary, Steve and Sue have been doing some tests in French, English and Maths. We have to determine the standardised mark for each student on each test in French, English and Maths, and work out who did better than the other two in each of those 3. And in part C we have to work out who got the best result overall, right? Okay, let's go. We'll do A, so we're going to do the French first. Mary got that, and it looks like she got exactly 1, which is right on the first standard deviation for that. What did Steve do? Oh, poor old Steve isn't too good at French, is he? Never mind, Steve. Hope you'll pick up in maths, maybe. There's Sue. She got, what'd she get? She got exactly on the mean, didn't she? Right on the mean. Okay, so it looks like Mary scooped the pool for the French test. Good on you, Mary. Okay, here comes the English now. This is Mary's English result. It's 7/8, which is 0.875. Pretty good result. Almost 1 standard deviation to the right of the mean. Steve got 39 minus 42 over 3, which is -1. Poor old Steve, he's not too good at English either. Probably doesn't like the arts much, the humanities. Sue, how did you go, Sue? That looks like a pretty good result. Yes, that's 0.7. That's not too shabby at all for English. Well done, Sue. So it looks like Mary's got the Guernsey again for English. Good on you, Mary. Killing them. Righto, what about maths? Now, right, Mary, how did you go? She got right on the mean. Right on the mean. Steve, how did you go? Oh, not too shabby at all, Steve. That's 5/4, 1.25. Now, that's a stellar result. A stellar result. What about Sue? Oh, no, she's gone less than the mean. She got -1/5, -0.2. So that's interesting, isn't it? So Steve gets the prize for the maths, doesn't he? Well done, Steve. Now, who is your best overall student, everyone? Give reasons for your answer. Well, I interpret that to mean who got the highest score out of any subject. And wouldn't you know it, the guys have come through. It's Steve by a landslide. Well done, Steve. Okay, so I would say Steve has the highest relative score of any of those subjects, okay, which was in maths. So good on you, Steve. Do you see how you do it, guys? You know, we're just comparing apples with apples when it looks like you've got apples and onions and pears and goodness knows what else, okay? And we're having some fun. All right, now what's this? Blood pressure now, goodness. The blood pressure, which is the systolic, which I think that's the higher one of the two, isn't it? Not being a doctor, I think it is. Among women of similar ages is normal, with a mean of 120 millimetres of mercury. I think 120/80 is what you're supposed to get, isn't it? Or 110/70. And a standard deviation of 10, all right, millimetres of mercury. Determine the percentage of women with a systolic blood pressure between 100 and 140. Okay, I can see what's going on here. I get this. Right, so how many standard deviations are we talking? And there's the graph. There's 120, and the sigma, which is the standard deviation, is 10. So to go from 100 to 140, what are we doing, guys? What are we doing? We're going 2 standard deviations either side of the mean, which means we're getting 95% of the population, aren't we? Very, very good. Okay? Do you get that? Of course you do. Thank you, Mr. Box. Right, I will do B now. Greater than 130, all right? 130. Now, where's that? There's 100. Oh, yeah, 130. Okay. So we're doing 1 standard deviation now, aren't we? Which is 68% of everything. Now, if you're doing greater than 130, the balance, after you take away 68% from 100, would be 32. And therefore, each of those tails, those left and right tails, would be 16% each, wouldn't they? Therefore, I'm saying that I think the answer to B is 16%. Voila. Like it? It's easy. Okay? Yeah, 16%. Thank you, Mr. Box. Now, we're going to do, where are we up to? B. We'll do C now. Greater than 120. Oh, that's easy. I know what to do. That's number C. Here you go. Look, here's your graph. Now, come on. You can look. You can read that off the graph. What is the percentage of women who will have a systolic blood pressure greater than 120? It is 50%. Yeah? There you go. There you go. Okay? Yeah? Very good. And what about the last one, D? Between 90 and 150. Okay, well, where's that on the graph? Ah, that's 3 standard devs, isn't it? 3 standard deviations. So, right, between a 90 and 150 means we're within the 3 standard deviation limits, which means I say that's 99.7, and I think that's right. Yes? Good man and good lady. So, you get it now? It's easy. It's really easy, isn't it, this stuff? Yeah. But it sets the tone for how to understand normal distributions, all right? Ah, what have you got to say, Mr. Light? Well, get back in your box, will you? Yes, I know, yes, you're trying to be funny, but you're not funny, okay? So, we'll go on. We won't be too unkind to him. Yes, that was very funny, Mr. Light. Thank you for your contribution. And we'll keep going. Now, determining normal probabilities, okay? So, how do you do that, ladies and gentlemen? Well, it's very, very easy, okay? You just have to know how to use your CAS handheld wonder machine, and I'm going to show you, okay? Here we go. Now, if you go into your menu and you go menu and then you select number 5, which is probability, that one, then you push the little across right arrow on that one, you then see a little entry which will say distributions, and then if you then go further, having selected distributions, you'll see 3 of them, okay, you'll see, and there are, you've got normal PDF, you've got normal CDF, and you've got inverse normal, okay? There they are. Now, the first one I haven't even ticked because it's not very useful. That is the normal PDF, but the normal CDF is very useful, and the inverse normal is incredibly useful as well. So they're the ones you're going to be spending quite a bit of time in their company, guys, okay? Now, let's just go into details with that. The normal PDF, okay, so what's that one? That gives the value of the probability density function itself for a given value of x. So why would you want that one? Well, I really can't think of much of a reason, to be honest with you. So I don't know. If someone would like to text me or let me know where you use that, I've never seen it used. So, but it's just I'm just telling you, it's there in case there is some usefulness for it somewhere, which I haven't discovered. Usefulness? No, not much. Okay. So, e.g., if you had mu is 30 and sigma is 7, then, and someone asked you what is the probability density function when x is 40, well, you'd be able to get your wonder device out and you'd be able to go into that. And it asks you to enter those 3 things, the x value, the mu and the sigma, and you just push the OK, and that one, and that one, and that's what you get, 0.020543 for some reason, which I can't think of for the life of me why you'd want that, but I'm willing to be corrected, okay, if anybody can think of a reason. But that's what you do, that's how you do it, right? Very little to no application for this feature there, as far as I can see, okay? Now, number 2, the normal CDF. Okay, now what that does is it gives you, this is a very useful one, this gives you the value of the cumulative density function, the cumulative density function, that means it's a probability, that is the area under the probability density function, f of x, for a given interval. Now, what am I talking about? Usefulness is very, very useful. Let's just give you an example. What percentile ranking is a student? Now I'm featuring your exams as a normal probability, a normal distribution situation, okay guys? So what percentile ranking is a student who obtains a study score of 30, secondly 35, thirdly 40, and fourthly 45 in their final exam subject, which we'll say will be mathematical methods, CAS, when mu is 30 and sigma is 7, which incidentally are the parameters for every single course study in your exams at the end of the year. Okay, so this is going to be a very interesting case study, right? Okay, let's do them. So you go into your calculator, you go menu, 5 probability, then distributions, and then you select What do you select? You select this one, normal cumulative distribution function. Okay? Or cumulative density function, probably. I don't know. Anyway, but that's what it is, yeah? Now, okay, so what you do is you select the lower bound is minus infinity, in other words, coming in from the left-hand side. Your upper bound is a study score of 30, so you want to know where you are if everybody is below you and you got a 30, okay? From minus infinity up to your score of 30, and the mean is 30 and the standard deviation is 7, and that's that one. There's the lower bound, upper bound. Mu's 30, sigma is 7. What do you get? There you go, that first one. That first one there in that list, you get 0.5, which is the 50th percentile. So you're exactly in the middle. You're exactly in the middle, okay? That's when you get, that's with a study score of 30, okay? The second one, 35, exactly the same process. And what do you get? Yeah, okay, that's that one. Now, what do you get for this one? You get the 76th percentile. Now, look how much that rocketed up. From the 50th, with only a 5-point increment in your study score, you get to the 76th percentile. Okay? What about with 40? You're up to the 92nd percentile. 92nd, you're ahead of 92% of the entire cohort in the state. If you get a 40. Okay, and if you get a 45, my goodness, you're in the heady heights of the stratosphere. You've got 98% of students are behind you. Okay, 98% of students are behind you. Now, this is very interesting stuff. Wouldn't you agree? I think it is. I think it's very fascinating, and I wanted to show you how to work it out. So I'm just putting in the answers there in the middle of the screen there. Okay, there they are. And there they are, okay? So now you can see the usefulness of the normal CDF, okay? So what does it do? It gives you the value of the cumulative density, the cumulative probability for a given interval, in this case, we're going from minus infinity. In other words, all of the curve up to and including the point that we're considering as the upper bound, okay? All right, here we go. Now, what's this other question here saying? What percentile ranking? Oh. What percentile... Oh, yes, I'm just reproducing the silly thing. Okay, now, my question to you is, in relation to what we just did on the previous screen, why do those probabilities percentiles go up at a much faster rate than the scores do, which we're incrementing by 5? 5 points each, from 30 to 35 to 40 to 45. Why did it go up from 50 to 76 to 92 to 99? In other words, it went up really, really fast from 50 to 76. Then it started to slow down a bit from 76 to 92. Then it slowed down a lot from 92 to 99. Why is that? Well, it's all revealed in the bell curve, and I want to show you why it is, okay? So, there's the study score of 30, which means you're at the 50th percentile. 50% of all students are behind you. Okay? Now look very carefully as I go from 30 to 35. Look. You see now, I'm now including that much extra area, e.g. probability. So, see what I'm doing? I'm adding 26% to that 50%. Now I think you can start to get the picture. You start to glean what's going on. When I go from 35 to 40, you see the height of the probability density function is dramatically plunging down. So with each equal 5-point increment along the horizontal axis, you're capturing less and less of the area, e.g. the probability. In other words, you've got less students you're competing with here. So with a 5-point increment, you're passing a lot more than you were before, because there's just less of them up here in the stratosphere. Yeah, see, there's only 16% in that block, and in this last block, 45, you've only got 7%. So that's what gets you up to the 99th percentile. So a lot of you students think, oh, gee, I want to get a 40. I want to get a 40 for this. Well, you know, you've got to understand that 40 might only seem like, 4/5 of 50, but you've only got 8% of students in front of you. 8% if you get a 40. That's not very many, so you've got to think about that, go a bit easy on yourself. All right, number 3. This one here is the inverse normal, which finds the value of x corresponding to a given cumulative probability where the lower bound is minus infinity. In other words, this is the reverse of the previous one, the normal CDF. With the normal CDF, you go with a given interval of the horizontal variable, and it gets you the probability which corresponds to that. In this case, however, you're going to go from the left-hand boundary, minus infinity, and you're going to go up to a given cumulative probability that you know the probability this time, and it'll give you the upper bound horizontal variable. That's what it does. Now, the upper bound. Okay, so finds the upper bound value of x corresponding to a given cumulative probability, knowing that the lower bound is from the left-hand side extremity, minus infinity. I'll show you what I'm doing in a minute. The usefulness, yes, it's very, very good. Excellent. Here's an example. What score would I need to get in my final exams to be in the 90th percentile? So you see what I'm doing here? I'm saying I'm going to give you the probability now. I'm going to give you the probability, and I want to know what score belongs to that probability, okay? All right, so you go through the old routine menu, probability, distributions, and this time you choose inverse normal, okay? Inverse normal, and you put in an area of 0.9 for the 90th percentile, an area this time, and you put in your mean of 30 and your standard deviation of 7, and what do you get? You get 38.97. You could call that 39. So, in other words, if you want to be at the 90th percentile, you've got to get a score of 39, a study score of 39, okay? So that to me, and people think, oh, gee, that's not a 40 though, is it? Well, my goodness, it sure ain't a bad score. That's all I can say. It's an excellent score. So there you go. Is this interesting? I think it's fascinating. So the score required is 39. Thank you, Mr. Box. All right, what have we got here? We have a normal distribution with a mean of 30 and a standard deviation of 7, as we've been doing. We've got to find k, such that the probability that x is less than or equal to k is 0.95. I can smell an inverse normal because I'm given the probability, I want the variable, okay? If you've given the variable and you want the probability, it's the other one, it's the normal CDF. Okay, we'll do A and then we'll think about B. Here comes A. Now, yes, there's the curve, and we want a 0.95 total area from the left. That's what we want. So what have we got? Do the old calculator routine. You get 0.95 for the area. You get mu is 30 and sigma is 7, and what do you get? You get that. And that is 41.514. So in other words, you've got to get a score of, well, they don't have half point scores, so it looks like you've got to get a 42. 42. You get a 0.95 area. It's actually 41.5, but you can call it a 42. Yeah. So that's 41.5, score of 42. Yeah. Okay. Good. Now what about B? What have we got to do for B? We've got to find C1 and C2 such the probability that our horizontal variable is between them as extremities of 0.95, where C1 and C2 are symmetrically spaced either side of the mean. Wow, that's pretty interesting. Here's my curve. Now, that's what we're talking about, guys. C1 is one extremity, C2 is the other extremity, and they're equally spaced on either side of the mean. So, I think we want, in between them, in between C1 and C2, we want to have an area of 0.95. So how many standard deviations is that, guys? Isn't it 68, 95, 99.7? Yeah, that's right. So therefore, we want 0.025. We want 0.025 on each of those tails, don't we? Yes, because we want 0.05 for the combined two tails. Yes, you know what I'm saying? You've got to halve each one of them individually to get the individual area at either extreme. Alright, so if you do that, what do you get? I've done both of them for you. Inverse normal. That first one is the inverse normal of this is my area, that's my mean, that's my standard deviation, and I get 16.3. Okay, that's not a very high score. And in this one I've gone for the 0.975 one, okay, with the same mean and the same standard deviation, and what did I get? 43.7. Okay, so there are, that is C1, that is C2 for me and you, okay? How's that? Yep, that's from minus infinity to 0.025 and I get that. That one there's from minus infinity to 0.975 and I get that. Are you still with me? Or have you gone to sleep? No, come on, wake up, not far to go now. Yep, that's the values. Righto, now. Alright, I think we're nearly finished now. Yes, I think we are. Good. So what percentage of students, I couldn't be bothered typing this one out because I was getting tired, so I just wrote it out for you. What percentage of students score between 25 and 35, right? 25 and 35 on their exams when the results are normally distributed with the same parameters, mu's 30 and sigma's 7. So, what would you say? Come on, have a guess. What percentage of students would score between 25 and 35? What do you think? Okay, lock it in. All right, let's go. We plug it into the calculator. Now, what are we looking for? What are we looking for? We are looking for a probability, aren't we? So if you're looking for a probability, you use normal CDF, okay? If you're looking for just a variable from a probability, you use inverse normal. You've got to get used to that, okay? So you ask yourself the question, what am I looking for? Well, I'm looking for a probability, so I'm going to use normal CDF, and these are the ones I'm going to put in. My lower bound is 25, my upper bound is 35, my mean is 30, my sigma is 7, and I'm going to get, what am I going to get? I'm going to get a probability. Yes, I am. There it is. 52.5%, which is over half. Over half of students get between 25 and 35. How do you like that? Pretty staggering, isn't it? Yeah, so there you go. Alright guys, that is the end of our little foray into all those three things that we did tonight, which were standardization, the 68, 95, 99.7 rule, and how to use your handheld wonder device to get the stuff that you want. Okay? That's the answer, and you're a star, and you'll go far. Of course you will. And I hope you enjoyed it. Now, go get them, guys. Go and do heaps of practice and get really, really good at this stuff. And we'll see you anon. Okay, bye.